So in our lecture yesterday, we just we started with the notation for vectors, and we saw that the same vector QP could be expressed into different reference frames. So we have frame 0. Usually the frame is represented like this. If you see the notation by Craig, usually this brace brackets, they come here. In the same way, if we are to represent so this is frame 0, and here we'll have frame 1. Frame 1 will be in red. So we saw that we could represent the same vector in different frames, frame 0 and frame 1. The components of the same vector in different frames would be different. So when you express the same vector in the frame 0, you get different components. When you express the vector in the frame 1, you get a different set of components. We arrange these components in a particular order, and we call it a vector. It's an array actually, matrix array, but we call it as a vector. And this representation will help us in doing programming using MATLAB or Scilab or other software which are similar, which are computational software. We also saw yesterday that these two representations of the same vector are related through this transformation, which is called as the R matrix. And the transformation is relating from the frame 1 to the frame 0. Okay? And then we set about working out the relationship. What are the components of this transformation? And this is what we got. We will analyze this part a little later. But before that, I would like to ask you, what is the need for doing all this? Why are we representing a vector in different frames? Why are we interested in this? So this is the first question that should have come to your mind. Now let us see. The reason for it is like this. Usually we have our manipulator, our robotic mechanisms. So we call it the robotic manipulator because it can manipulate objects. So say we have a robotic mechanism, which is, I'm just drawing the skeleton of that. It's composed of several links like this. You have several links, maybe like this. Usually we call this, this could be the base. We could have the base here. And could be on a fixed base or it could be even moving. We have these links, which we are familiar with links from theory of machines. So these are all links. We usually take them as rigid bodies. And these links are connected to each other through joints. So we have maybe one joint here, which is something like your waist joint. Okay. So we may have a joint here. We may have another joint here. We may have a joint here like this. We may have another joint like this. We could also have prismatic joints. So maybe we would have another joint like this. So depending upon the configuration, we have joints. Now, the kind of robotic manipulator which I have indicated here, this is called as a serial chain manipulator. It's a serial chain mechanism. And the reason for that is understandable because the links are in series, one after another, one connected to the other, and it's like a chain. So serial chain manipulator. Okay. So this configuration is a serial chain manipulator. We are talking of robotic manipulators. We also have other configurations of manipulators. Like you may have a configuration like something like you may have a configuration like this. Could also have more than so this configuration you may be having like the way we hold our pen, for example, you may have a tool here and you'll be able to orient to position the tool. So here we have a configuration which we usually call as parallel manipulator or closed chain. So these are, so here you may have joints here. You may have a joint. So this configuration of manipulators is serial chain. It's a closed, it's a parallel manipulator or a closed chain manipulator. Okay. Closed chain. This was actually an open chain, serial chain or an open chain. So this is a closed chain. We also call it as parallel uh, parallel manipulators. Now these are just configurations and each configuration has its significance. Okay. These, irrespective of what is the configuration of this manipulator, we have the links of the manipulator which are composed of rigid bodies. So usually these links are rigid bodies. This is the usual configuration. And these are here, we have here joints. These are joints. And we may have different kinds of joints. So uh, we may have revolute joints, we may have prismatic joints. So we may have different categories of joints, and using a combination of revolute and prismatic. So we may have spherical joint, different kinds of joints are possible. So we have links, which are usually rigid bodies. We have joints, and the question is now, suppose uh, we are interested in the motion of the tip, let us say, of this point here. Okay. Let's say that there is a tool which is connected here. So if there is a tool connected here, usually we call this the last link as the end effector. So this is our end effector. So here you may have a tool. Now we may be interested in positioning this tool, positioning it accurately, and also orienting it accurately. So the first question is, we should understand about its position, how to specify its position. So that is why we have we have to make use of the representation of position, and that is why we began with the position vector. Position, sorry. Okay. Now every rigid body, say a point on the rigid body, we can specify its position. Usually we specify this position with respect to a reference frame. Now, in our case, let us say that we have a reference frame. Um, Let us take a reference frame. So we have this, let us say we have a reference frame here. It could be located anywhere. So we have the axis of the reference frame. So this is one of the axis. This is, let us say, another axis. I'm just indicating the positive directions of those axes. And we may have yet one more. So we have the axis. We can also specify we can identify this frame. So let us say that it is an inertial frame, it's a fixed frame. We can say that this is the frame 0. It's our base frame. It's also called a base frame. It is fixed. So we have the origin of the frame here, origin of the frame 0. And here, let's say we have the tip. So let's say there is a point P here, and we are interested in specifying the location of this point. So we have to We have to work out this vector. How do we work out this position? So this is the position of this point P as seen from the frame 0. Okay. So here we have the position of the point P with respect to the frame 0. When we write this graphically, see, this is the vector which we have, have represented here, position of the point P with respect to 0. Now, when we represented this graphically here using this vector, we did not write the frame of expression because it makes no difference. Whatever is the frame of expression, graphically, the vector is this itself. Okay. It's when you try to represent it mathematically that you have to specify the components. So the representation of this position vector, the frame of reference becomes important when you have to specify uh, which is the frame with respect to which you are specifying you are representing this point, this position vector. Now, it's convenient for us. You see, normally this manipulator will move in space. It can have arbitrary motion or programmed motion. It can move in space, and so the links will also move. Now, suppose we fix a frame on each of these links. So we fix a frame on link 1. Say, let us say this is link 1. We have link 2, link 3, and so on. Okay, we have n links. So the numbering goes on like this because it's a serial chain manipulator. It goes usually from the base to the tip. So if we fix a frame on each of these links, as the manipulator maneuvers, you will find that the frame which is fixed on the link also moves. Okay. Now, it's convenient for us to understand the location of any point on a link with respect to its own frame. But as this point moves, we need to understand what is the position of this point with respect to the inertial frame. If the position of this point in the respective link frame is provided. Okay. So this is the reason why we try to understand the representation of position. And because we are going to use the matrix representation, we are going to do computation. And so we are going to write this, we are going to specify this mathematically as a vector. So graphically, we don't write this frame of the frame of expression. But here, when we represent it in mathematical form, we have to specify the frame of expression. And then we mention the components. The components, the Cartesian coordinates in this case. So these are the components of this vector. See, they are scalars. So these are the components. Okay. And we represent it as a column array. So matrix, 3 by 1 matrix. We are already familiar with this representation in another form. We have been writing this as xp using the unit vector of the frame 0. So the unit vector of the frame 0, that is the I. So let's say if this is x naught, this axis is y naught, and if this is z naught, then the unit vectors associated with these directions, let's say this is the unit vector I naught. We have the unit vector j naught and the unit vector k naught. The magnitude of these unit vectors is 1. Okay. And they are mutually orthogonal. Orthogonal means they are mutually perpendicular to each other. And what we are doing here is representing, we are considering a right-handed Cartesian coordinate frame. Okay, so usually we will use, in fact, in all our work, we will use the right-handed Cartesian coordinate system. What do we mean by the right-handed Cartesian coordinate system? It means that if you consider your right hand, you have the x. If you have the x direction like this, you have the y direction like this. You turn from the x towards the y, you get the positive direction. The thumb points towards the positive direction of z. So I to j will give you k. So we have made use of the right hand. Okay. So this frame, this representation, you have already done this in your 12th standard uh, or maybe earlier 11th standard or even 10th standard, the right-handed Cartesian coordinate system. But now we are just going to represent it here. So we have this plus y e j. This scalar is the length from here to on this component which we saw yesterday, and this is the unit vector indicating the direction. And here we have z e and okay. So this is the representation which we are familiar with. But now, because we are going to use matrix methods, we will represent the same vector like this. We'll just write the components here. Of course, we have to specify the frame of expression. And you see these components are in the frame 0. Now I'm sure that this slide of yesterday makes better sense to you. So we represented this frame 0. We represented the position of, we represented this position vector in terms of the components of frame 0 and also the components of frame 1. And we saw that these components are different and we could relate them. Now, we tried to find out what is the relationship between these components in our last lecture, in our lecture yesterday. And for that, we proceeded from the basics, absolutely. We specified this vector in the frame 0 and also in the frame 1. And then we took a dot product with I naught on both sides. And we could get the vector xp, okay, in terms of its components expressed in the frame 0. Here, we could get the components of the frame of the vector, same vector, but expressed in the frame 1. And the relationship was obtained through a transformation. So we got a matrix here. This matrix that we got is our R matrix. Okay. So we represent it using represent this notation like this. I think it looks too cluttered, so I'm not going to show this here. I think you can understand it, so I'm not going to make changes.
Yes, sir.
Yeah. Now let us look at this matrix. Before we look at this matrix in detail, let us look at another aspect also. Let us we'll make a copy of this. Now suppose we are interested. Suppose we are interested in taking this vector to the left hand side and this vector to the right hand side. That means we are interested in knowing the reverse. So here, suppose we are interested in knowing if we have on the left hand side the position vector expressed in frame 1, how is it related to the position vector in the frame 0? From this relationship, it's very clear that we will have to just inverse this matrix, isn't it? So we can send this to the other side, pre-multiply it by the inverse. Do you agree?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So you can see we can proceed exactly in the same way as we did yesterday, but now we can write the relationship so this relationship would become R, which is actually relating from 0 to 1. Okay, but we see that this R0 to 1 is just R1 to 0 inverse. Okay, so I will just reduce the size of this that we have done yesterday. Yeah. And we can see here that R1, R0 to 1, R0 to 1 is actually just the inverse of 1 to 0. Do you agree?
Yes, sir.
Yes, sir.
So far, you
Yes,
have
sir.
understood. But now, let us look at this matrix. Let us look at this matrix in a different way. We will see it slightly differently. Just like we did yesterday, now we will yeah, so I think it's easier for us. We'll shift this entire vector here, and this part here, this part here will erase. Now let us see what we have here. So now take let us consider this equation over here. Okay, the first one. In fact, we'll also erase this one. Okay. So now, suppose we are interested in obtaining this component. What should we do? All that we have to do is take the dot product on both sides. We just want to retain this component. So what should we take the dot product with? I1,
I1.
I1 vector. Okay. So here we will take I naught dot I1. Okay. Multiplied by XP. Okay. So I naught dot I1. Here also we have to take dot product with I naught. So this will become J naught dot I1. So this multiplied by this element. Okay. Plus here also we take dot product with I1. So here we get K naught dot I1. Okay, so this is this component multiplied by this, that is when you take the dot product on both sides, then we get the next one. So in the same way, we will be able to, sorry. We'll have another row here, and we'll have another row here. and we'll fill up the components of these. So here we will have, in order to obtain the second row, that is, what is this? So in order to retain this element here, we'll have to take the dot product with J1. So here it will become I naught dot J1. This will be I naught dot, sorry, this will be J naught dot J1, and this will be K naught dot J. Here likewise we will have I naught dot K1, here it will be J naught dot K1, and K naught dot K1. Okay, so now what we have got is the position of the vector P. In fact, yeah, the position of the vector P with respect to Q expressed in the frame 1, and this is equal to this matrix. So this matrix, this entire matrix, operating on this vector. Okay. So this matrix here is R, but now you see you are going from 1, from 0 to 1. So this is frame 0, 1. Operating on this vector, the vector that we have here. This is the position vector of P with respect to Q, but expressed in the frame 0. Okay. So you can see that R0 to 1 is actually just the inverse. Now let us have a look at the structure of these two matrices. The structure of the matrix here, R0 to 1 and R1 to 0. Okay. So here we have R1 to 0. If you look at this carefully, look at the columns. Look at the columns of this. You will find something very interesting. You will find that each of these columns
The transpose matrix.
just look at this column. Look at this column. Yeah, you're right, it is the transpose. Each one, the two transformations are related to each other. You can see here. So So you have these three columns. Now, what are these three columns? If you look carefully at this, you will find that here you are having I1 dot I naught, I1 dot J naught, I1 dot K naught. That means you are resolving the unit vector I1 along the three directions of the frame 0. Three directions represented by the unit vectors of frame 0. I naught, J naught, K naught. So you are just determining the components of the unit vector I1 and writing those components in terms of the frame 0, directions of the frame 0. Okay. So we can write this as the unit vector I1 expressed in terms of the frame 0. So this is the first column. Okay. So this is our first column of the matrix R1 to 0. Then if you look at the second column, you find the same thing. But now you have J1 dot I naught, J1 dot J naught, and J1 dot K naught. So here now you are taking you are representing the unit vector J1 in terms of the components of the frame 0. So you're resolving it along the three directions of the frame 0. So this becomes J1, unit vector J1, represented in terms of the components of the frame 0. Okay. And here likewise you have the unit vector K1 represented in terms of components of frame 0 or resolved along the frame 0. So this is actually your R matrix. If you look at the rows of this matrix, what do you observe? What do you observe are the rows of this matrix? You can see this is I naught dot I1, I naught dot J1, I naught dot K1. So you're resolving the vector I naught along the three directions of frame 1. But now because this is a row, that means you have to take the transpose. So it becomes, so the same thing you can also write as so you can write it as I1, the unit vector I naught represented in terms of frame 1. But because it's a row representation, so we will have to take this transpose. Okay. Likewise, you have J naught as the second row. So here you have J naught, unit vector J naught expressed in the frame 1. This is our second row. And unit vector K naught expressed in frame 1. This is our third. So this is the same matrix that you have here, but written in terms of different unit vectors in different frames. Okay. So you can either write it like this or like this. Okay. Now, when you see the other side, when you see over here, you find that now the unit vector I naught is being resolved along the directions of the frame 1. So this can be written as I not resolved along directions of frame 1. This is our first column. And the second column is J naught resolved along directions of frame 1. And K naught resolved along directions of. So this is the same matrix. This is actually R 0 to 1 okay, and we know that R 0 to 1 is actually the inverse of R 1 to 0. Okay, so it's the same thing, but this is also, if you look at the previous slide, you can see that it is just the transpose. So it is just the transpose of R 0 to 1. Isn't it very interesting? This is just the transpose. Now this is a very special matrix. It doesn't happen for all the matrices. It is a very special matrix, and it happens only in this for the R matrix, that its inverse is actually its transpose. Okay. And this property actually is also called as the orthonormal property. And why do we call it orthonormal? We'll discuss it in our next class. I think we are out of time. So we'll discuss about this property, about the orthonormal property. So we have the orthonormal property of the R matrix. So we'll discuss about this in our next lecture. Do you have any queries so far? Please let me know if you have been able to follow this.